So children, so this is part 2 of the sample paper. Question number 8 is state Einstein's photoelectric equation and using it explain any two laws of photoelectric emission. So the question is of 3 marks. How to answer it? Let us see. So first we have to write Einstein's photoelectric equation, which is easy, which is this equation, that how much energy is falling on a metallic surface will be used up in two ways. Number one, work function, and remaining energy will be kinetic energy max of the coming out electrons. So that is energy of the photon, you should write like this, is equal to work function. Work function you can elaborate, energy required to eject an electron, and the remaining energy will be maximum kinetic energy of the ejected electron. So this is the equation that you need to write, and then this can be written as energy incident photon is equal to work function is W naught, maximum kinetic energy is kinetic energy max. Then this can be further written as energy of the incident photon can be written as h nu, work function can be opened as h nu naught, kinetic energy max will remain kinetic energy max. So this is the equation that needs to be reported, but then again the symbols that you have used you should tell. This is the frequency of incident photon. So frequency of incident light you can say, incident photon also you can say. Then it is nu naught. What is this? This is threshold frequency, minimum frequency. So coming to the second part of the question, which says using it you will have to explain any two laws. So this is of 2 marks. So how would you do it? You will pick up these two laws particularly. There are 4 laws, but these two can be shown mathematically that it can be explained on the basis of Einstein equation. This is Einstein's equation. So let us see. There is a definite cutoff value of frequency below which electrons cannot be ejected by any substance. So basically this is law that gives the concept of cutoff frequency, or you can say threshold frequency, below which electrons will not emit, photoelectric emission will not take place. So how would you do this? How would you elaborate it? You will pick up that equation once again, that energy is equal to work function plus kinetic energy max. You will use it, and using it you have to produce this law. So you will use it, h nu is equal to h nu naught plus kinetic energy max. Now you will say let the frequency of incident be less than cutoff. If the frequency is less than cutoff frequency, you can say this is less than. So what does it mean? If you will take this side, h nu minus h nu naught is equal to kinetic energy max. H is common, nu minus nu naught is equal to kinetic energy max. Now you can see nu is less. So if we are subtracting this, like this is less number, 6 minus 7, this is more number, so it will be negative. This will be negative, so this is negative. So kinetic energy is coming negative. So if kinetic energy is coming negative, that means the process is not occurring. Kinetic energy negative means nothing. The process is not occurring. So process is not occurring if frequency is below threshold frequency, and this is what we are writing here in the law. So this mathematics needs to be done to prove it, that this law is obtained, is supported from Einstein's equation. This needs to be done. Okay. So if the frequency of incident light is less than cutoff frequency, then kinetic energy comes negative, that is no photoelectric emission. So this is first law. Let us pick up the second law. So this is the second law. So second law is this, which can be shown on the basis of Einstein photoelectric equation. Kinetic energy of the emitted electrons depend upon frequency of the incident light. Okay, so again you will be picking that equation, Einstein equation. What is that equation? E is equal to work function plus kinetic energy max. So you can see this is h nu, and this can be opened as h nu naught plus kinetic energy max. So h nu naught will go that side again, and this is kinetic energy max. It is common, nu minus nu naught is kinetic energy max. So from here you can say that bigger, this is fixed, this is always constant, this is also constant, this is Planck's constant, and this is cutoff frequency, threshold frequency fixed. H and nu naught are constant for a given metal, for given substance, given surface, given metal, basically metal. So it means kinetic energy is dependent on whom? Kinetic energy max is dependent on nu. What is nu? Nu is the frequency of incident light. So that is what it is written. Kinetic energy depends upon the frequency of incident light. So you will have to choose two laws wisely, which can be mathematically shown coming out of the Einstein photoelectric equation. So see, there are two more laws, total 4 laws of photoelectric emission, but 2 can be shown successfully out of the mathematical equation. So that is why I am leaving these 2 laws. But then again, if it comes 4 laws, you need to be written, you have to write all 4. But 2 can be shown coming out mathematically. So let us shift to the next question now. So the next question is define stopping potential. We have to define stopping potential, and we have to plot the graph of stopping potential against frequency of the incident radiation. Then they have added more question to it. How is stopping potential affected if intensity of radiation is increased, keeping its frequency constant, above threshold frequency. So let us discuss the question. First of all, first part of the question says define stopping potential. So we know stopping potential is the potential at which the motion of the electron stops. The motion of the electron stops. Okay, it stops. Kinetic energy is 0. Okay, so that means no photoelectrons are emitted. So photoelectric current is also 0. So you can see it is the value of retarding potential, negative potential between the two plates, two electrodes, which is sufficient to stop the motion of electrons. So stopping potential is that potential. Now coming to the next part of the question, which is plot stopping potential, that is V0 against frequency of the incident radiation. So let us see for the plot, second part of the question, we have to plot the graph for stopping potential and frequency. So for this I will pick Einstein equation once again. So you can see this is my Einstein's equation. Energy is equal to work function plus kinetic energy max. Energy I have opened as h nu, work function h nu naught, and kinetic energy max I have opened as EV naught, where V naught is the stopping potential. Now to show this part, like you should know this part, how it has come. So definition of potential is work upon charge. Now when potential is stopping potential, work will be kinetic energy max. So charge of electron is E, right? When potential is stopping potential, work is kinetic energy max. So I've replaced, and when E will come this side, this is V naught actually, so E will come this side, so it is EV naught is equal to kinetic energy max, and that is why I have written here. Now h nu naught will go that side, so you can see h nu minus h nu naught is EV naught. Now I have written EV naught this side and this equation this side, no problem. So V naught can be written as V naught alone. This V naught needs to be made alone. So E will go that side and that side down. So my equation that is ready is V naught, that is stopping potential, is equal to E comes down. So H by E times frequency and H by E times nu naught. Now H nu naught is work function. Again you can make it if you wish. So this is the equation. Now this is comparable to the equation of straight line. This is y, this is x, this is m, and this is intercept. So this equation is comparable to equation of the straight line, that is y is equal to mx plus c. So it means the graph between stopping potential and frequency would be a straight line. So the plot would be this. This is stopping potential. This is frequency. You can see this frequency, this which is x variable is frequency. Here it is stopping potential, and graph will not start from 0 because there is an intercept on negative y-axis. So this is the value of the intercept is W0 by E. So it will start from here, dotted line and then dark line. So this is a graph. Let us see about the third part of the question, which is how is the stopping potential affected if the intensity of radiation is increased, keeping its frequency constant. So frequency is constant, intensity is being increased. So see, stopping potential is EV, matlab kinetic energy max is equal to EV0, that we know. And we have seen in the first part of the question that kinetic energy depends upon frequency. So if we are keeping frequency constant, stopping potential is going to be constant. So no matter if you increase the intensity, how high, if the frequency remains constant and it is above threshold frequency, stopping potential will not change. So stopping potential depends upon frequency, not on intensity. So stopping potential, no change if the frequency remains constant, but it has to be more than threshold frequency. So let us understand this part of the question. Question is, ground state energy of hydrogen is this, that we know. If electron is making transition from this to this, calculate the wavelength of the light emitted. This is one. And which series does it belong? So we will come to the general formula of energy in nth shell. Is this for hydrogen? This is for hydrogen. Okay, and it is in electron volt. Strictly in electron volt. Okay. So first energy is given as this 0.85. Keep it here. Keep it here in place of this. The minus 13.6 remains as it is and n square remains as it is, right? Now minus and minus are cancelled. Fine. Now n square would come this side. This n square would go this side. So you can see I've written here. And minus 13.6 minus was gone. 13.6 upon this. When I divided, I got it as 16. So that means n is 4. Similarly, again I've picked up the same formula and I've kept this particular energy here. Again minus gone. So there is no need to write minus. N square will come this side, 3.4 will come down. So when I divided, I got 4. So it means n is this. So it means from this to this, the electron is jumping from. So electron is jumping from n is equal to 4, fourth shell to second. And when we return to second, the spectral series, to which series does it belong? You must remember that it will be Baumol. So we have answered this question. To which series does it belong? Now what is left? We have to calculate the wavelength also. We have to numerically calculate the wavelength. So you can see I have written it here again. The electron was making a transition from this energy to this energy. So I will subtract the two energy in such a way that it comes positive. Okay, this is how I remember. So we have substituted lesser value first and then minus this value. So minus will be plus, and when we will subtract, we'll get it this. But again, keep in mind this is an electron volt. So in order to find out the wavelength, we know that energy will be opened as h nu, but keep in mind that this needs to be opened, this E. So you can see this I've opened here. Now it is in joules. The energy which was in electron volt, now it is in joules. So energy is opened as h nu is opened as C by lambda. We have to tell lambda. We will substitute the value of h as this and value of C as this. And this side is already there. We can calculate wavelength and report an SI unit, that is meter. So you can see so many parts were there in this question. We had to tell the Bohr's statement of angular momentum, which is this. Then we have to calculate the wavelength, this wavelength, and then we have to tell which series does it belong. So for 3 marks, enough has to be done. So let us see the next question now. Question number 10 is define nuclear fusion and nuclear fission. So that you know, this is direct question. So nuclear fission is splitting of a heavy nucleus into two average, and fusion is joining of two small into an average. Okay? So both sides are getting average. Here heavy is splitting into two average, and here two lighter and two small are joining up to form an average. Then you have to see this one example for each. So you can learn any example. Okay, generally we learn this one. For fission, learn this equation. Uranium 92-235 that everyone knows. Slow moving neutron. This is slow moving neutron. And then this is fissile state that you not need to write. So don't write this. Directly you can write krypton, barium with charge and mass. You have to remember charge and mass, and 3 neutrons are released, which are fast, and this much energy. We write it as 200 million electron volt, so either 200 or the accurate value. But again, the equation is important. You should memorize all the charge and mass. This state needs not be written, but if you are writing, good for you. Thermal means slow, that is room energy, and fast is fast, just fine. So this equation is for fission. Now coming to picking up an equation for fusion. So we can pick up any equation from here for fusion. Generally we learn this. I learn this. Deuterium, light nuclei 1s2, helium 3, and 1 neutron, and this much energy. You should memorize the value of energy to score full marks. So let's see question number 11, which is identify the circuit in the block diagram X below. So you can see this diagram. Sorry. This diagram. We have to identify what is this, what is X. So we can see this is full wave like this, and here we are getting only half wave. So what is here? Which equipment they are going through? They must be facing some half wave rectifier. So here is half wave rectifier. We have to draw its circuit diagram, and we have to explain its working. So working I will cover in a separate video. Like for important topics in semiconductor, I will make working of half wave rectifier, full wave rectifier separately. So right now only circuit diagram. So you can see this is complete wave. Here we are getting only half wave, and output is obtained across load resistance, V output. So this is a circuit diagram, and this diode is acting as rectifier. This diode is acting as rectifier. So let's see the question number 12. So now the last question, case study based question. Read the following paragraph and answer the following questions. Galileo is credited for using telescope to observe celestial objects. He made use of refracting type telescope. However, refracting type telescopes suffers from many disadvantages. These were either minimized or eliminated in later versions to come. Newtonian and Cassegrain telescopes belong to reflecting type category. Radio astronomy has undergone wide-scale development from installation of GMRD to launch of James Webb by NASA of late. So let us see what are the questions framed. Which of the following is correct statement? Refracting type telescope makes use of lens. Yes, correct. Objective lens of telescope has larger aperture, so that is correct. Objective lens needs to have larger aperture and larger focal length than compared to the eyepiece for telescope. So these two are correct. Colored images not obtained. No, color images can be obtained due to spherical aberration. Both A and B. So yes, both A and B are correct. So this is option. So let us go through next. A refracting type telescope refracting means both lenses. In real, adjustment has. Now see, generally we know about normal adjustment mode, right? So let's see if it is normal or something other. So final image is formed at least distance, then final image is virtual, enlarged and inverted, then length of the telescope is this, and all of these. So see, basically, because they're talking about the final image is formed at least distance, so it means this is not normal adjustment, this is real adjustment mode. So it is different from normal adjustment. So in normal adjustment, final image is formed at infinity, so this must be something else, where image is formed at least distance of distinguishing. So this is correct for real. So when we draw the diagram, then we know that final image is formed virtual, enlarged and inverted. So that is also correct. You can see from the ray diagram. And length of the telescope is less, yes, because it is equal in case of normal adjustment mode when it is formed at infinity. So all are correct. So get to the next question. Which of the following statement is correct? GMRT stands for Giant Meter Wave Radio Telescope or Giant Microwave. So meter wave is correct. They must have mentioned in the paragraph. This is correct. And this is a space technology launched recently. So A and C are correct. But see, GMRT, when I went through this topic, when I tried to explore about this topic, then I found that this is Giant Meter Wave Radio Telescope, and it is one of the largest telescope. And what's more interesting is that we have it, India has it, and it is located in Pune, to my surprise. And along with India, 40 other countries uses it. So that is something to be proud of. And moreover, so this GMRT has 30 fully steerable gigantic parabolic dishes. So, and moreover, it is awarded, it is the third Indian facility that is awarded by IEEE, Institute of Electric and Electronic Engineers. After, first is Cbse and second is C.V. Raman. So this is the third Indian facility. So I'm very astonished and found it very captivating news that IEEE is awarded, and that too like after J.C. Bose and C.V. Raman. J.C. Bose got it in 1895 for generation and reception of radio waves, and C.V. Raman in 1928. So children, these are the things we should be updated with. See, they have included a question which is so much related to us, and I'll tell you about GMRT. It was used in 2018 to locate most distant galaxy ever known, which is located at a distance of 12 billion light years. It was discovered by GMRT. So we have it, India has it. And in February 2020, it helped in the observation of biggest explosion in the history of universe. Okay, that is known by this supercluster explosion. So if you wish, you can find more about it. So this particular question I found very interesting. So let us get to the next. In reflecting, it is reflecting. Till now all the questions are based on refracting. Reflecting type telescope, concave parabolic mirror is used at. So yes, objective. And if you remember the ray diagram, it is like this, and rays are collected by the objective. So now coming to this, what is the magnifying power of telescope? So if it is written like this, it means they are talking in normal mode. So in normal mode, it's f naught by Fe or minus f naught by Fe. So you can see out of these, you will be a little confused. So it has to be minus f naught by Fe. Finally, in derivation, we get this. So that's all. Thank you so much.